So, hi class. So this is another lecture in organic chemistry, and I think this is our third lecture. There are two more after this. So this lecture is going to be on drawing isomers and recognizing isomers. And if you remember when we studied complex ions and coordination compounds, we talked about isomers. And there are two broad classes, structural isomers and stereoisomers. So that's what we're going to look at today in this lecture. So I'm going to share my screen and we'll get on with the PowerPoint. We're going to do two worksheets today, worksheet 37 and 38. So isomers. So our objectives this lecture will be to recognize and draw isomers of organic compounds. And there are two broad classes of isomers, like I said, structural isomers. And we're going to look at two kinds. One is called skeletal, one's positional. And skeletal is like the difference between, remember we talked about organic compounds are built on a framework of carbon atoms, and the carbons can be arranged linearly in a chain, or they can have branches, or they can have rings. And so the structural isomers derive from the different skeletons of the carbon framework. And then stereoisomers, remember there's geometry called cis and trans, and then optical isomers. And these we covered previously in complex ions and coordination compounds, so they're similar. And worksheets 37 and 38. So here's a concept map showing how these isomers are connected. And question isomers, well, just as a reminder, isomers are compounds that have the same formula, molecular formula, but different structures. So I have a little side path there that says not an isomer. Well, anything that has, if the molecular formulas are not the same, they're not isomers. Okay, if they're one atom different, they're not isomers. So the molecular formulas have to be identical for two compounds to be isomers. So as we go through this, we're going to look at constitutional isomers first. That's another name for a structural isomer. Some books call them constitutional isomers, and that's the connections between the atoms. And in an organic compound, they're different. And there's an example of some constitutional isomers in that frame underneath that box. It's they're all C6H12 compounds. In one of them, you see two of them have a branch. I mean a straight chain of 6 carbon atoms in a row. The only difference is that the double bond has moved. That's what we call a positional isomer. The position of that double bond has moved. And then in the third one, there's a branch. So it's a 5 carbon chain. So actually the carbon skeleton is changed. And it has one carbon off the 5 carbon chain, one carbon branch. So in this case, we have two positional isomers, but they're structural isomers, and then one what we'd call just a structural isomer that's different from the others. And our stereoisomers, there are two kinds. We're going to talk about the cis-trans isomers that we heard about previously in chapter 19, and then also optical isomers, which are mirror images that are not superimposable. So we'll continue. Let's go on. So constitutional isomers first, AKA structural isomers. They have the same formula with different arrangement of atoms. They have the same number of atoms bonded in a different order, kind of another way to say that. So we'll look at a simple compound C4H10, which is called butane. This has the formula CnH2n plus 2, so we know it's an alkane. So all the bonds in this butane are single bonds. And the simplest butane is just 4 carbon atoms in a row, showing here on the left. And here we have the expanded structure, which is kind of a Lewis structure. It's the model. It's a picture of a model that you would make. And then we have the condensed structure. So CH3, CH2, CH2, CH3. It clearly shows the carbon atoms bonded together in a straight chain. And then we have the skeletal structure, which is a zigzag structure on the. So all these structures in the top row represent butane. The name of this compound would be normal butane, C4H10. C4H10 is butane. So butane is the molecule that has 4 carbons in a row. Now, if we take these 4 carbons, these C4 carbons, and we make a chain with 3 of them, but then put 1 branch off of it, we have a new molecule. And the 3 carbon chain is called propane. So this is a derivative of propane, and it's called methylpropane. If you want to know the name, it'd be called 2-methylpropane. And that's because when we name change, you number the chain from one end, so it'd be 1, 2, 3, and the methyl group is on the 2nd position. Methyl means 1 carbon side chain, if you will, or 1 carbon substituent. So we have 2-methylpropane. So they have different names, but they have exactly the same formula. And remember, that's one characteristic of isomers. That's how you distinguish them, is they have, if you don't have the structure and all you have is the names are different. Now, if you draw a structural formula, like a condensed formula, you can clearly see that they're different. Or if you have a skeletal structure drawn, you can see that those are different. But the names are different too. The only thing that's the same is the C4H10. Their molecular formulas are identical, and they have properties. Their properties, their boiling points are different, their melting points are different, they have different reactivities. So they're quite different compounds. So let's look at the next one. Our next slide. Oh, there's some names there, isobutane and isobutane. So butane, the C4H10, the straight chain molecule, there's some structures of butane. So in the first row here, you can see butane. I'll draw a circle around it. This is the Lewis structure of butane, showing all the bonds, all single bonds. It's an alkane. The carbon atoms are sp3. The bond angles between the bonds around each carbon are tetrahedral and 109 degrees apart. If you had made a model of that, it'd be a really wiggly molecule. It'd be a zigzag. The carbon chain would be in a zigzag. So that's why sometimes you see butane drawn like this. And not this little thing at the end. That's not there. But we have some condensed formulas of butane shown below the expanded structure, the Lewis structure. And in the first row, we have the condensed structure that you would probably draw if you change the Lewis structure into a condensed structure. But then next to it, we have all these other structures. Well, all those others are also butane. And you can tell, even though they're drawn differently, they're still butane because all the carbons are connected in a row. You can see if you go from carbon to carbon, you still get this kind of a connection between them all. Even though they zigzag, in actuality, they do zigzag. So those are all butanes, just different structures, just represented a different way, drawn a different way. They're not different structures. They're all the same structure, but just drawn differently. So you have to be able to recognize that. That's kind of a little trap you can fall into if you don't understand these structures. If we had models, if we could make models, you could easily see that. You could make a model to look like all of these, but then when you compare them, they would be the same molecule. So here's the C5H11. So we've increased we said butane. Let me go back. So there's two isomers of butane, structural isomers. And let me add something here, that you have to have at least 4 carbon atoms, 4 or more, to have structural isomers. So if you only have 3 carbon atoms, there's only one. There are no structural isomers because you can't make a branch. So C3H8 there's only one molecule. C2. So this is alkanes. But if you take you have C3H8 and you take 2 hydrogens away and make it C3H6, well, then you've got opportunities for isomers. But as far as alkanes, saturated hydrocarbons, you need to have 4 or more carbon atoms to have isomers. So this next slide, we have C5H12. That's still, again, it's our CnH2n plus 2. So this is still an alkane. It's an open chain alkane, no rings. And let's see how many isomers we make. Remember with C4H10, we only had 2 isomers. Well, C5H12, there's the first compound, pentane. That's how you normally draw it. So if you're asked to draw isomers of this, you would just draw 5 in a row, begin with, and then add the hydrogens. And then maybe you draw 4 in a row and add a branch. Okay, so we have 5 in a row. And then we have 4 in a row with a branch sticking off of it. And then we have 3 in a row with 2 branches. So when we add one more carbon atom to come up with the formula C5H12, we end up with 3 isomers. So we've added one more. And as you add carbon atoms, you have more and more ways to arrange those carbon atoms. You end up with more and more isomers. So isomers of C3H8 are those isomers. So take a look. This is C3H8. I'm not sure if when you think about these, no, these are not isomers. These are just different ways of drawing the same structure. And this was like that example of C4H10 I showed previously, where you just write the bonds in a different angle, but you still have 3 atoms connected in a row together. In every case, 3 atoms in a row. And like I said, if it's an alkane, you can't have isomers for C3H8. There aren't enough atoms. There are none. But if we take away 2 hydrogens and make it C3H6, so this would be the generic formula of a cyclic alkane, or the formula of an alkene with 1 carbon-carbon double bond. And those are the 2 isomers, the 2 structures we can write that are different. So here's 2 structural isomers of C3H6, cyclopropane, and propylene, or propene, one is propene, propylene or propene, another name is propene. The pro stands for 3 carbons. When you take organic chemistry, you're going to learn a new language, and it's the language of organic chemistry. So if you haven't heard of these before, these are all ways to name and describe organic compounds. So we have cyclopropane on the left, C3H6, and propylene on the right. These are clearly structural isomers. They don't look the same. They have way different properties. They're all saturated though. Let's see, well, the cyclopropane is saturated. So this is carbon double bond, that's an alkene. And later on, we're going to talk about families of organic compounds, and the alkene is the first one we're going to talk about. We've already talked about it. So we've already learned one family. It's an organic compound with a double bond. It's called an alkene. Okay, so here we have C3H6. So that's a CnH2n and an O. So we're adding an oxygen to it. So the most common molecule is acetone. So acetone, you've probably heard of acetone. Another name is propanone. It's a ketone, another family of organic compounds. And this is the structure of acetone, CH3, C double bond O, CH3. I think we've seen this before. And this has, a pi bond, the sigma bond there, 2 sigma bonds there. The carbon is sp2. It's a trigonal planar and all that. But because oxygens have 2 bonds, we don't have to put the oxygen on the central carbon. We can put that oxygen on the right carbon or the left carbon, move the hydrogens over. We can put the oxygen between carbon atoms, C3H6. Remember, we had C3H6 before, that forms a ring. We can make a ring. We can put double bonds. Whoa, as soon as we had that oxygen, C3H6, we had 2 isomers. We had an O, and let's see how many isomers we have. Whew, lots of isomers. Look at all those isomers just by adding an oxygen atom to our C3H6O. So in our homework, I've got a homework assignment, a worksheet assignment, to draw all the isomers of C3H6O. So I'm going to skip that. You can come back to this PowerPoint to look that up if you want to see how many you can draw. So let's see. So let's go on. So that's the end of constitutional or structural isomers. Let's go on to geometric isomers now. So our first, we're going to talk about geometric isomers, and those are called stereoisomers. Oops, sorry. So stereoisomers, also known as there are 2 kinds of stereoisomers. So we're going to talk about stereochemistry and stereoisomers, and the stereoisomers are geometric, which are cis strands, or optical isomers. And so to make stereoisomers, you have to have some feature in the molecule that will create a different geometry in the molecule. So the first feature, and when we're talking about geometric isomers, is alkenes. So alkenes, many alkenes can exist as cis or trans. It's the double bond, that's the feature that creates the opportunity for different geometric isomers. And the reason is because the carbons can't rotate around the double bond. The double bond freezes the rotation. If you have a single bond, you can rotate the carbon atoms actually move. You can think of them as spinning almost like a propeller if it's a single bond. If it's a double bond, it's frozen. And so the atoms connected to that double bond are frozen in space from one to the other. They can't just rotate, and if they're on the opposite sides of the double bond, they just can't rotate and become on the same side. So that's where we get the cis and trans. So the simplest alkene is this one. It's called ethylene. Well, you can't have geometric isomers in, well, I guess you can in ethylene, but not in this molecule because all of the atoms attached to the double bond are the same. But if we changed it a little bit, if we put a chlorine, I'm going to cross this off here. These are hydrogens. If we cross off the hydrogen and instead put a chlorine here, cross off this hydrogen and we put a chlorine here, well, now these chlorines are on the same side of that double bond. And that turns out to be a cis compound. So this would be a cis because the chlorine's on the same side. It can be on the top side or the bottom side. if you kind of look at the plane of this double bond, we could say both chlorines are above it. If we remove one of those, and I'm not sure how to erase that chlorine, but I'll draw another structure. So we have another one like this. I'll draw it over here. Carbon, double bond, carbon. We put a chlorine up here, and then we put a chlorine down here. Oops, that's not a chlorine. CH, chlorine. We put H here, and then H here. Now the chlorines are on opposite sides of that double bond. One chlorine's below it, one chlorine's above. I'll call this the below, and this is the above. Not written very good. This is the above. This is the below, sort of. So when they're on opposite sides of the double bond, this is trans. So this is a trans molecule. So I'm going to show more of those as we go on. So if we talk about, we're looking at hydrocarbons, only carbon and hydrogen. That last one had chlorines in it, so it wasn't a hydrocarbon anymore. But if we just talk about hydrocarbons, the first alkane, the longest alkene that can have cis and trans isomers is butene, 2-butene. So you have to have 4 carbons, and the double bond has to be in between the second and third carbon. And then on the left side here, we have the cis isomer with both CH3s above the double bond. And on the right side, we have one CH3 below, one CH3 above. So we have cis on the left and trans on the right. Let's look at some more. So they don't have to be carbons. Like I showed in the last example, we could have chlorines. We can also look at the H's to decide if it's cis or trans, the hydrogens. So the hydrogens are on one side, makes them cis, and on the other molecule, the hydrogens are on opposite side. So here's another example of an alkene, another hydrocarbon. And like I said, they don't have to be hydrocarbons. You can have chlorines, iodines, fluorines, but if things are on the opposite sides, they're trans. If they're the same side, they're cis. And there's another designation we're not going to go into, because you can have more atoms. You can have fluorine, chlorine, iodine, and methyl group all on the same double bond. Then there's another way to designate the geometry and the stereochemistry of that double bond. These are rather simple molecules that we can designate cis and trans. So there are different stereoisomers that you can't just designate cis and trans. There's another way to describe it. It was kind of like the FAC. Remember when we talked about complex ions, there's the facial and the meridional. Still can't say that very well. The MER and the FAC isomers in complex ions. Well, you have that kind of stereoisomers also that are kind of beyond the cis and trans isomers. Anyway, on the left side, if you look at this chain, here's our double bond. So you look at the double bond. You can look at the hydrogens. There's 2 below. So that makes it cis. Or you can look at the side chains, the alkyl groups. They're not side chains, but they're the groups attached to the double bond. They're on the same side. So that makes this cis. And then down below, these big groups attached to the double bond are opposite sides. And so that makes it trans. And the last example here shows a different molecule. It's just 3 carbons with a double bond. And what it shows is that on one carbon of the double bond, here's 1 carbon of the double bond, it has the same groups attached. So you have an H, 2 H's, 2 hydrogens attached to it. Well, if you have a situation like that, you can't have cis or trans. That negates the possibility of having cis or trans. So if 2 groups are the same that are attached to a double bond, you can't have cis or trans. And those 2 groups don't have to be hydrogens. They could be chlorine, chlorine. They could be CH3, CH3. They could be C2H5, C2H5. There's lots of, if they're the same, group, then you can't have cis or trans. So the last statement, not all alkanes exist as cis or trans isomers. So another way you can have cis or trans is if you have a ring. And so if you have a ring with two groups attached, if the groups are on opposite sides of the ring, you have a trans ring compound. If you have groups on the same side of the ring, you have a cis ring compound. This shows a natural molecule, beta carotene. You may have heard of beta carotene. Well, beta carotene is a huge natural occurring molecule in carrots. It's the orange carrot color in carrots and other fruit. And it's the orange color you see in leaves in the fall. That's beta carotene. Well, beta carotene is, when we have a double bond, we call that unsaturation. Let's see what's going on here. Sorry about that. Oops. Sorry about that. Let me start up from here. Here we go. Okay, so beta carotene is has a lot of double bonds. And remember, every time you have a double bond, it's called unsaturated. And so this has a lot of unsaturations. And when you have a lot of unsaturations in a molecule, it tends to be colored. And so that's why beta carotene is orange. There's some other, this is a natural occurring compound. There's some other natural occurring compounds shown on the side that have double bonds. You have alpha pinene, you have limonene, and just like they sound, alpha pinene is found in pine trees and limonene is found in lemons. Anyway, let's look at some of these double bonds. So if you have a double bond in a ring, like alpha pinene, you don't have cis or trans. So that double bond doesn't confer cis or trans. What confers cis or trans is the things attached to the ring. So if you had two groups attached to the ring that were on the same side or opposite sides, then you could have cis or trans. But in alpha pinene, you don't. So both in alpha pinene and limonene, those double bonds don't confer any cis or trans isomers on the molecule. However, in beta carotene, let's look at this double. So double bonds in the rings don't, like I said, don't make cis or trans isomers, but double bonds in a chain do. So here's a double bond. Look at all these double bonds in beta carotene. All of these double bonds in beta carotene in the chain are trans double bonds. And that's because the chain starts on one side of that double bond, then extends through the opposite sides. And when you draw a structure, it's a zigzag structure. So trans double bonds give zigzag structures to chains. On the other hand, a double bond in a cis double bond in a long chain gives a bent chain. And this happens to be the structure of a cis fatty acid. And fatty acids are in all of our cells. They make up the membranes of our cells. And cis fatty acids are the naturally occurring fatty acids. And it kind of makes a U-turn in the chain. There are also such things called trans fatty acids, and trans fatty acids are very unhealthy. And in a trans fatty acid, you get that zigzag in the chain that we saw previously. And so just little thing, cis and trans compounds are very common in nature and are important. So we have some health effects. The cis fatty acid is a healthy fatty acid. The trans fatty acid is an unhealthy fatty acid. You've probably heard about avoiding trans fats. That's what it is. So lastly, we're going to talk about optical isomers. And optical isomers, remember optical isomerism has to do with mirror images, non-superimposable mirror images. So two isomers that are mirror images of each other that are non-superimposable. Now another name, I don't know if we mentioned this before, but they're called chiral objects. So if something is an optical isomer or has this property of having a non-superimposable mirror image, it's called chiral. So, and that's not, it looks like chiral, it's called chiral. Okay, the way you pronounce this This word is chiral, okay? So what are chiral objects? Chiral objects are like your hands. So if you try to superimpose your hands one on the other, you can't do that. And I think I have a little animation here. I'm not sure why it's not working. Come on. Click. Okay. There we go. Okay, you can't put the left hand on the right hand. We all know that anyway. So the chiral objects have the same number of atoms. They're connected together the same way, but they're arranged a little bit differently in space. So they have this property that the mirror image won't superimpose. So mirror images won't superimpose on each other. So in order for an object to be chiral, it has to have what's called a stereocenter or a chiral center. And that's the same as one carbon atom has to be chiral. So if, it doesn't matter how many atoms you have, but if you have one chiral atom in the molecule, that makes the molecule chiral. So we're going to look at what makes a carbon chiral. I think lastly, we talked about the optical isomers are called enantiomers. Okay, the mirror image isomers are called enantiomers. Next slide. So this shows the simplest chiral carbon. And the simplest chiral carbon is a carbon atom. There's a carbon atom in this molecule with 4 different attachments, 4 different types of molecules, 4 different types of atoms attached to it. So it doesn't have to necessarily be an atom. It could be a group of atoms. But in this example, you have a hydrogen, a chlorine, an iodine, and a bromine attached to the carbon atom. So those are 4 different. That makes this atom chiral. And if you switch 2 of them, if you switch like the iodine and the chlorine, you get this molecule on the right side, and that's the mirror image. So that's how you go from one chiral molecule to the other, is just to switch 2 of this to the attached groups. And if you do 1 switch, you make the enantiomer. If you do 2 switches, you get back the original molecule. So that's a little trick you can play with simple chiral molecules, is you can change from one to the other just by doing these switches. An odd number of switches makes the enantiomer, makes the mirror image isomer. An even number of switches returns you to the original molecule. The image on the right just shows how the mirror images are not superimposable. So the mirror image of just a summary of chiral compounds. The mirror image isomer of a chiral molecule is an optical isomer called an enantiomer. It must have 1 or more chiral centers to be optically active, 1 or more. So at least 1. The chiral center is an sp3 carbon atom, so that's important. It has to have 4 single bonds with 4 different ligands attached. So that's kind of a nice way to say it. That's statement 3 tells you what a chiral center is. Let me go back. Statement 3 tells you what a chiral center is. And it's tetrahedral because it's got 4 single bonds. Chiral molecules are asymmetric. So if you only have 1 chiral center then it's always asymmetric. So there's no, but if you have 2 or more chiral centers, you have to look at this asymmetry characteristic. So it has to be asymmetric for the molecule to be chiral center. That means there's no plane of symmetry. So I'll show you an example of what that means. So chiral centers are also called stereocenters. So sometimes you hear that term, stereocenter. So how do you determine if a molecule has 1 or more chiral centers? So so you can include the lone pair. So is the electron lone pair geometry? So that means is if you remember, just if it has 4, first of all, it has to have 4 single bonds around the the atom. So it has to only have single bonds. Double bonds or triple bonds negate the atom from being chiral. So it's to have 4 single bonds. Well, those are what they're called. That's the electron lone pair groups. Okay, so if you have 4 single bonds, the geometry is going to be tetrahedral. That's what that first one means. So it has to be tetrahedral at first. So it has to be tetrahedral. And that includes a non-bonding pair of electrons. So are the 4 ligands on the atom different, including the lone pairs? So if you have a lone pair, and carbon doesn't have a lone pair, but nitrogen does. So there are nitrogen-containing compounds that can be optical isomers because the lone pair, nitrogen with 3 single bonds and a lone pair, is tetrahedral. So if the 3 ligands connected to the nitrogen plus, let me put nitrogen here. We have nitrogen, 3 bonds, and a lone pair. If these X, Y, and Z are different than nitrogen, that nitrogen is a stereo center. So then if we go down, if everything's true, going down the left side, it's chiral. If if there are not 4 ligands on the 4 different ligands on that tetrahedral carbon or nitrogen, then it's achiral. So that's a flow chart you can use to decide if a molecule is chiral or not. So here's a few examples. So identify each as chiral or achiral. So let's look at A. So A, we have a carbon in the middle, and it's tetrahedral, so it follows the first. Are all 4 ligands attached to the carbon, are they different? Yes, they are. We have C2H5, CH3, Cl, and H. Yes, so this would be chiral. A I'd say is chiral. How about B? Oh, we have a carbon, this tetrahedral. Are all 4 ligands different? And the answer is no. We have 2 hydrogens. How about the last one? We have a carbon in the middle, and we have all 4 ligands different. And so it looks like that can be chiral too. So it's a chiral, A is chiral, A is chiral. So it has a mirror image isomer and an antimirror. B is achiral. If it's not chiral, it's called achiral. And remember I said there actually is a plane of symmetry in this molecule. And it's hard to show it because it's tetrahedral, but the plane goes between the hydrogens and it goes through the chlorine and the CH3. And then C is chiral. So what about compounds with rings? And here we have our cis trans again. So let's look. So remember, here we have a ring. So let's look at these carbons. Do we have any chiral carbons here? And we do. So I put stars next to the chiral carbons. These are the chiral carbons up here. This is what the stars are referring to. 4 single bonds around those. There are 4 different attachments. So if you look at the carbon, if we go to the left side, if we go clockwise around this ring, we have CH2. And if we go counterclockwise from this carbon, we have a CH3. So this is different. So the attachments on the ring are different. Then we have a CH3 and an H, and they're different. And so we have 4 chiral. So we have 2 chiral carbons, 2 stereocenters in both. So right away you say, okay, that fits. So the last rule, because we have more than one stereocenter, is you have to check for symmetry. So is there symmetry? So let's split this down split this molecule in half, and there's no symmetry here. It's different. So I would say that the trans molecule here is probably chiral. If you look at the cis and you split it down the middle, there is a plane of symmetry. The left side and the right side are the same, and I think I show that a little better with that. There's a plane of symmetry in the cis, so that makes it achiral. So that's our conclusion. Okay, so that's the end of the lecture. So I want to go to I'll stop the share, and we'll go straight to this worksheet. So the first worksheet, 37, is about structural isomers. So I have that written there. And the second worksheet is about stereoisomers. So in this one, there's a few rules about drawing compounds. And on this worksheet 37, the whole idea is to draw some structural isomers with the guidelines that are given. So there's 3 problems, 1, 2, and 3. And I'll work on, maybe I'll do number 3, for example. Okay, and then I'll let you guys do 1 and 2. So some of the rules at the top are rules we've talked about before for chemical bonding in organic compounds. Carbon forms covalent bonds. It forms 4 covalent bonds. It forms single, double, or triple bonds. It can bond to itself and change branches and rings. And it can bond to other non-metal elements. In this exercise, the other non-metal, the other non-metal elements are nitrogen, or hydrogen, nitrogen, and oxygen. So we're just going to look at forming compounds with these atoms, other atoms besides carbon. So the other thing you have to remember, we kind of have this here, is that oxygen, and let's see, I wrote this, oxygen can form single and double bonds, and nitrogen can form single, double, and triple bonds. Okay, so I'll just read these exercises. So the first one, it says, draw as many structures as you can. In fact, all of them say that. Draw as many structures as you can. Well, that's kind of open-ended. So what I might say is draw a structure that contains each of these elements for chemical bonding for each of the types of atoms are in the compound. So number 1, we only have carbon and hydrogen. So what I would say for number 1, draw a molecule that has a straight chain carbon, draw an alkane, draw an alkene, draw an alkyne. Alkyne has a triple bond. So the first problem, number 1, is only carbon and hydrogen. It says you have 4 carbons and an unlimited number of hydrogens up to 10. So you can for the first problem, you can have up to 10 hydrogens. Now, if you form a ring, you're only going to have 8 hydrogens. If you form an alkene with a double bond, you only have 8. If you form a triple bond, you'll only have 6. So as you keep adding double bonds and rings, you have fewer number of hydrogens. So I would say try to draw a linear compound, a branched compound, a ring compound. Draw one with a single bond, a double bond, and a triple bond. And so do all those combinations. So if that's 3 times 3, you may have 9 different molecules, at least, that you can draw. So there's a lot of isomers. When you have 4 carbons, you can draw all kinds of isomers when you're adding single, double, and triple, using single, double, and triple bonds. So I'll let you do that. I'll draw the first one. I'll draw one. So I would draw 4 carbons in a row, and then I add all the hydrogens to that. So that'd be my C4H10, and then I'll just draw the carbon skeleton, and then you could add the hydrogens. It's just carbon and hydrogens. I could add a double bond. Okay, and then I'd add hydrogens. And when you have a double bond, this central carbon has 3 bonds already, so there's only 1 hydrogen. I could add a triple bond. So there's an example of a straight chain with a single, double, and triple bond. So then I would say go on and draw a ring with single bonds, a ring with a double bond, a ring with a triple bond, and add the hydrogens. And that would probably be it. But there's lots of other compounds. I could draw a carbon here with a triple bond and a double bond in it, or 2 double bonds. There's lots of combinations. So I'm not sure how many molecules are possible there, but it's got to be 20 or 30, different compounds. So just try to draw as many as you can. So you do number 1. I've started you off there. And number 2 is in the PowerPoint. So I want you to do this one, but look at the PowerPoint. Okay, and so I'll do number 3. I'll try to fill in number 3. There's a lot of space on this worksheet for me to work on number 3. So number 3, we have 3 carbons and 1 nitrogen. And when you have nitrogen, because nitrogen has an odd number of bonds, you don't follow that CN2 2N plus 2 rule. You have an odd number of hydrogen. So we're going to just add, I would say up to, I think up to 7 hydrogens, and we'll see. Okay, so the first one, it would be carbon. I'm just going to make my straight chain, carbon, carbon, carbon. And then I'm going to put a nitrogen at the end. Then I have 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh yeah, 9. Made a mistake there. 9 hydrogens. So 9 hydrogens. So that's one molecule. And I think when I draw this, I'll put the bonds in, but I'll leave the hydrogens off to make it a little easier to draw, or else I can draw a line angle. So next, there are no isomers, so I can't make any isomers of the chain, but what I can do is I can put the nitrogen in between the carbon. So I can do this. So there's another molecule. That's a structural isomer. And then I'm going to fill in the bonds where the hydrogens go. So that's another one. I can make a ring out of carbon. So I can make carbon, 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 carbon. And then I can put a nitrogen off one of those carbons. So there's all our bonds. And that's another one. I could make a ring and put the nitrogen in the ring like this. And then I've got 1, 2, 3 bonds to the nitrogen molecule like that. Let's see, what else can I do? Well, then I can do all those same structures again and put a double bond in there. So I could do my the carbon like this. I'm going to do a skeletal structure. So like that. So there's my 3 carbons, and then I put my NH2 here. So there's another one. I could put the double bond in the middle like this, and then put NH2. And here I made a trans molecule. And so I can make the cis, which would look like this. Okay, there's another isomer. I could do a triple bond and then have a C, let's see, triple bond with an NH2. There's another one, triple bond with NH2, semicolon. And then, you know, I can go on and on. So I have a triple bond, I have a double bond, I have a ring. I can't do a branch. This is sort of a branch. This is sort of a branch. You can do a branch with the nitrogen, put the nitrogen off here. So this is a branch. I'll do a condensed structure here. H3. So there's another one. And, you know, there's really, I haven't done a double bond to the nitrogen. I want to do single, double, and triple bonds to the nitrogen. So let me do a triple bond to the nitrogen, N, C, and that's called a nitrile. Then it goes CH2, CH3. And this carbon here has 4 bonds to it already. So the NC bond, remember this is sp hybridized. So we have 2 pi bonds and 1 sigma bond in the triple bond. I didn't do the nitrogen double bond, so I can do that underneath. I'll do a NH double bond C, and then there's an H and CH2, CH3, and it can go on and on and on. And I've just drawn 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 molecules, and that's probably only just touching the surface when it's that open-ended an assignment. So in the PowerPoint, remember, those are just structural isomers. I think of C3H6, structural isomers of C3H6O. That's what's in the PowerPoint. But if you did an isomer of C3H8 or C3H4, you get lots of different. So I just said any number of hydrogens. So 3 carbons, 1 oxygen, and the rest hydrogens. So the hydrogens can go from probably 2 up to 8. So hydrogens can be 2 to 8. So try to draw a couple of others that are not on that PowerPoint. All right, that's our structural isomer exercise. So let's look at the other stereoisomer exercise. So the structural isomer exercise is actually a lot more complicated than stereoisomer exercise. Stereoisomers are a little more restricted, not quite as open-ended. So here's a flow chart that shows the kind of it's like the flow chart on the PowerPoint that shows how you decide what kind of stereoisomers you have or what kind of isomers you have. So I'll just let you read that and go on to the problem set. So in this problem set, we have just 3 problems, and this is a fill in the blanks. So on the, what I have is I want you to write 2 isomers for 1, 2, and 3. Actually for 1, the 2 isomers are already written. And the idea is to write down to describe what kind of isomer it is. And then for problem 2, we have a C6H12. Oh, so for problem 1, I want you to write the formula. So the formula of both of these has to be the same. So column 1 is the formula. And for 2 and 3, it's already written. Column 2 is the kind of isomer. Column 3 is one isomer and the second isomer. And so I'll let you fill in the boxes for problem 1. I will do problem 2, and I'll have you do problem 3. So problem 3 is a compound with a stereocenter. So I'll just circle this. Let me zoom in on this a little bit. So here's your stereocenter problem 3. It's that carbon. So that's in the middle. And then you have 4 ligands, CHBRF. That's not enough ligands. So I'm going to have to add a Cl. Shoot. I'll fix that in the on the internet. In Canvas, I'll fix that formula. So you have to have CHBRFCl. And I think this is the same chiral molecule that is in the PowerPoint. So I want you to draw the optical stereoisomers with this formula. So I'll let you do that one. So I'll do this and draw the geometric isomers of C6H12. So C6H12, that would be a ring. So if I just drew the structure that comes to mind immediately for C6H12, that's something that looks like this. Okay, it's a cyclic molecule, or it could be like this. It could have an alkene. 1, 2, 3, 4, 5, 6. So it could be like that. So we can draw 2 stereoisomers. I'll draw them both. So one could have a ring, but it can't be a 6-membered ring. It would be a 4-membered ring with two carbons attached to it. The other one could be if we put a double bond, not in the end, but in the middle, we can have cis or trans. So let's start with the double bond. So I'm going to draw 2 cis-trans stereoisomers here. So isomer 1 could look like this. And this would be my trans. And I'll put trans isomers in that box. And isomer 2 would look like this. 1, 2, 3, 4, 5, 6. You always have to count the carbons after you draw a structure, make sure you have the right number of carbons. So, and this will be my cis. And then if I wanted to draw a cyclic molecule that has cis and trans, the trans would have one molecule, one group pointing up. So I'll go like this. I'll say this one is up in the air above the ring, and this one is below the ring. So there's my two methyl groups. I can have them on adjacent, or I can have them on opposite. So I could have them here and here, or here and here. That's okay. So this is my trans. Remember, this whole box is for trans. My cis would look like this. I'll draw my cyclobutane, it's called, and I'm going to put my two methyl groups on the same side, so they're pointing up like that. So it looks like they're on the same side. So that's my cis right there. So there's a couple ways. There are more cis and trans isomers you can draw from C6H12. So that was in the instructions. Geometric. And there's a little hint, only cyclic or CC double bond compounds have cis and trans. So that's what I drew. So there's a couple of other possibilities. If you want to practice, you could do that too. So that's pretty much the end of the lecture on stereoisomers and optical isomers. Well, structural isomers, stereoisomers, which include optical and geometric inorganic compounds. And so that's all for now. So good luck. If you have any questions, check in with me at office hours on Thursday.